Hello class, today we're going over combining lessons 8.1 and 8.2, and we're going to talk about drawing geometric figures and solving problems using scale drawings. So we got a lot of vocab words we need to get down today, so make sure you guys are pausing this video and writing down everything on these definitions here, just like we did in class. So for our first definition, we have a scale drawing. So a scale drawing is an enlarged or reduced drawing of an object that is proportional to the original object. So here we have a little example for us, right? So we have a smaller house and we have a larger house. And we're told that these are scale drawings. So basically, this is our original house right here, and it is 8.5 inches tall. And this is our enlarged house, and we don't know how tall it is. But we do know that for every 2 inches we have 5 feet. So we were given the ratio here for every 2 inches over 5 feet. So 2 over 5 is going to be equal to our 8.5 inches of the smaller house over however many feet. We don't know yet, so I'm going to put a variable here. All right, so obviously we can cross multiply these, right? So 2 times x is 2x, and 8.5 times 5 would give us 42.5. Oops. 2x is equal to 42.5. And then we'll divide both sides of our equation by 2 here, and we would get x is equal to 21.25 feet. So that means that this building right here would be 21.25 feet tall. So how are we going to use this in this chapter? Well, basically, we're going to be giving you a smaller version and a larger version, or vice versa, and you're going to have to find out how tall something is based on the other one. Or maybe we'll give you 2 items, and you'll need to find the scaling factor based off those 2 lengths there. All right, so I told you there's a lot of vocab words. We're not done yet. So next we're going to talk about drawing geometric figures. So we got 8 geometric figures, and I'd like you guys to get down all of these. So let's start with a rectangle. A rectangle has 4 right angles and 2 sets of parallel or equal sides. So if we're drawing it, it looks something like this. So every single one of these angles are a right angle, even though it doesn't look like that. These 2 side lengths right here are going to be parallel. We show a parallel side by doing a little arrow like that there, as well as these 2 sides also being parallel. And then finally, they have to be equal as well, right? So this side has to equal this side, and this side right here, these 2 outside sides have to equal each other. So next we have a square. And a square is very similar to a rectangle in that a square also has 4 right angles. So each one of these is a right angle here. The only difference with the square is these are all equal sides here. So in a rectangle, we have something where it is 4 right angles and 2 sets of equal sides. For a square, we have 4 right angles and every single side is the same. So you might be wondering right now, well, does that mean that a rectangle is in fact a square? Well, no, a rectangle isn't. A rectangle isn't a square, right? Because not all of the side lengths are equal. However, all squares are actually also all rectangles. So a square is just a more specific version of a rectangle. All right, next we have a triangle, right? And there's a ton of different triangles. However, the one thing that is true for all triangles is they all have 3 sides, and then all of these angles right here, A, B, and C, would all sum to 180 degrees. So the sum of A plus B plus C would be equal to 180 degrees. And then lastly, we have a kite. So a kite has 2 pairs of equal sides that are adjacent. All right, so that means they're next to them, right? So basically, it'll look something like this. It'll look like a kite, right? Where this side is equal to this side, and these 2 sides are equal as well. So we have 2 pairs of adjacent sides that are equal. All right, so those are our first 4 geometric figures there. Make sure we're getting those all written down. Don't be afraid to pause this here if I'm going a little fast. But now I'm going to go on to our next 4. So another one is a circle. I hope we all know what a circle is. If we don't, then we might need to do a little research here. But a circle, right? A circle is just a circle. Don't know how to describe a circle without saying circle. All right, next we have parallelogram. So parallelogram is a 4-sided figure with 2 pairs of equal parallel sides. So it can look something like this, right? So as long as these sides are equal and parallel, and these sides are equal and parallel, then this would indeed be a parallelogram. Next is a trapezoid, and a trapezoid is a quadrilateral with only one set of parallel lines. So if we're drawing something like this, we have a trapezoid here, right? Because both of these sides are parallel. However, notice over here that these sides are not parallel, right? This side is not parallel to this side. And I suppose I should mention too, parallel means they're heading in the same direction and they will never intersect. So well, I kind of took that for granted there, but a parallel line or a set of parallel lines are two lines that are going in the same direction and therefore will never intersect. And lastly, a rhombus. So a rhombus is a parallelogram with opposite equal acute angles and opposite equal obtuse angles and four equal sides. So if we had something that looked like this, oops, that's not to scale at all. All right, something like this here, right? So all of these sides are of equal length, and then these opposite angles, these obtuse angles are opposite each other or across from each other, and these acute angles are also across from each other. So that right there is a rhombus. All right, so again, make sure you guys are writing all of these definitions down. Don't be afraid to pause the video, but now we're going to go get into some examples here. So let's start with this one. Example 1. What quadrilaterals can you draw that have two side lengths of 9 and two side lengths of 4? All right, so a couple of ones here, right? For starters, what I think of right off the bat is a pair of two equal sides here. It's a rectangle, right? So I could draw a rectangle here. We don't know that these angles are equal there, but we totally could say they are. So we have side lengths 9 and then side lengths 4 here. So a rectangle is a possibility. Could also draw a parallelogram, right? Because a parallelogram has two sets of equal sides. So we could say that this side length is 4, 4, and 9, 9, because a parallelogram has two sets of equal sides. Gosh, some of my lines here are pretty bad. All right, and I believe we have one more. What about a kite, right? We could do a kite like this. So we could say that these both have side lengths 9, and these both have side lengths 4, and this would be a picture of our kite. So we got three different quadrilaterals we could draw on this one here. All right, another example for us. A four-sided sandbox has more than two right angles, two side lengths of 2 feet, and two side lengths of 5 feet. What is it? Well, I'll just tell you guys a trick. If something has two or more than two right angles, then it automatically has four right angles. So we know right off the bat that this is going to have four right angles. All right. So now we should ask ourselves, is what figures do we know have four right angles? Well, that means it's either going to have to be a square or a rectangle. But wait a second. It tells us that we have two side lengths of 2 feet and two side lengths of 5 feet. So we already know that a square has all equal sides here. This one does not have all equal sides. So that means a rectangle is our only choice for the figure we are drawing here. All right, now let's get into some practice with some scale drawings. Or maybe we've got one more, sorry. A friend is building a four-sided garden with two side lengths of 19 feet and exactly one right angle. What quadrilaterals could describe the garden? All right, so it's a little bit of a tricky one here, right? We only have one right angle. So if we have one right angle, we're probably going to be looking at a trapezoid, I think. Yeah, trapezoid here, right? Two side lengths of 19 feet and exactly one right angle. All right, so we got our one right angle right here. We could say that this is 19 feet up top, 19 feet right here. And then we don't know what the other two sides are here, but we don't really care because this is a trapezoid right here with one right angle, and we got two side lengths of 19. So a trapezoid was our answer here. Okay, so now we can get into some scale drawings here. So on a map, 1 inch equals 5 miles. Two cities are 8 inches apart on the map. So what is our actual distance? So we have a scaling factor here, right? So our scaling factor tells us that for every 1 inch, we go 5 miles, right? So for every 1 inch, we're 5 miles apart. Well, here we were 8 inches, right? So 8 inches apart times our scaling factor here, which was 5. So 8 times 5, which would be equal to 40 miles. So if something was 8 inches apart on our map with a scaling factor of 1 inch to 5 miles, that means that this person would be 14 miles apart here. So two cities are 14 miles apart. All right, do another scaling factor one here. So a drawing of a barn measures 1 inch in the drawing to 2.5 inches in real life. If the barn has a width of 3 inches in the drawing and a height of 6.5 inches, what are the actual dimensions of the barn here? So for every 1 inch, we have 2.5 yards. So we have a 1 to 2.5 ratio. So let's start with our width, right? So our width was 3 inches. So we're going to take that 3 inches and we're going to multiply it by 2.5 here. So 3 times 6 would be 3 times 2 would be 6. And then 3 times 0.5 would be 1.5. So we'll add those together here and get 7.5 yards. But we also have to do the height, right? So our height was 6.5 inches times the same 2.5 scaling factor here. So 6 times 2 would be 12, and then 5 times 5 would be 0.25. Let's see what we got here. 6.5 times 2.5 equals 16.25. 16.25. So that means that our height of our barn was actually 16.25 yards. Alrighty, we got one more example for us here. So let's finish it up strong. The scale drawing for a rectangular playing field is 2 inches equals 5 feet. Write an equation you can use to find the dimensions of the actual field, where x is a dimension of the scale drawing and y is the actual field. Assume I don't know, I must have forgot to finish typing that one there. All right, so our y is our actual field, right? So I'm going to start with y equals. Now, our x is the dimension of our scale drawing, right? So our x here, whatever our scale drawing is, and we're going to multiply it by 5 halves, because that's our scaling factor here. It's 5 feet. 5 feet per 2 inches. So we got this here. We want to turn it into a fraction, which would become 5 halves there. You would just put your expected amount or the real amount divided by the drawing amount. So for a formula here, we have y is equal to 5 halves x. Or basically what we're saying is the value of our real life drawing will be equal to 5 halves times our scale drawing there. So 5 halves times the smaller drawing will equal our real life drawing. Alrighty, so in conclusion today, we learned about some geometric figures, right? We learned about rectangles, squares, triangles, kites, circles, trapezoids, rhombus, and parallelograms. So there's quite a few there. And then lastly, we learned about using scale drawings and writing with scaling factors. So make sure you guys get this all down in your notes using what we learned in class 2 yesterday, at some point in the past. Other than that, everybody have a great rest of your day. I will see you all in class tomorrow. Bye-bye.